Welcome to Our Future in Space. In this podcast, we explore the technical, economic, social, political, and ethical considerations of moving humanity into the solar system to work, play, and ultimately live. Our species is at an inflection point in its evolution, where we now have the ability to sustain life off-planet in low Earth orbit and soon throughout the solar system. This is happening for several reasons: the falling costs of launch, the exponential growth of computation, the rapid commercialization of low Earth orbit, and a broadening interest in in the uh, in the concern that humans are outstripping our planet's resources. Do we merely survive or expand outwards and thrive? I'm your host, Dr. Jeff Greenblatt, the Vice President for Science and Research at Orbital Assembly Corporation. And I'm here with my guest, Jeff Greason, who is from Electric Sky and the Tau Zero Foundation. How are you doing today, Jeff?
Just fine, thank you.
It's great to have you here.
Great to be here.
A little bit about our guest. Jeff is an entrepreneur and innovator with 25 years experience in the commercial space industry. He is the chief technologist at Electric Sky, developing long-range wireless power for propulsion and other purposes. And he's chairman of the Tau Zero Foundation, developing advanced propulsion technologies for solar system as well as interstellar missions. He has been active in the development of commercial space regulation and legislation and served on the Augustine Commission of 2009, which you'll have to tell us a little bit about perhaps later, Jeff. Jeff was also the co-founder of XCOR Aerospace and served as CEO from 1999 until 2015. Previously, he was the rocket engine team lead at Rotary Rocket and an engineering manager in chip technology development at Intel. He holds 28 US patents and has recently published papers on novel space propulsion concepts, some of which we'll get into today. He's also a governor of the National Space Society. Jeff Greason, it is a pleasure to have you here today.
Thank you, sir.
Let's dig into today's headline topic, and I'm sure we'll touch on other things as well, advanced propulsion. So you've been working on this topic, it looks like most of your career. Maybe you can tell us a little bit about what first attracted you to it and how that's evolved over the couple of decades.
Yeah, because I don't come from a propulsion background. I started my career as an electrical engineer before I got bit by the space bug and decided to make a new career out of it in the 90s. And really, what's made my approach a little different from some people is that I'm not a propulsion aficionado, so to speak. I just have problems in space I want to solve. I'm only interested in it for what it can give us. I'm not for what it is. But everything you do in space, I teach now advanced propulsion for Kepler, and I tell my students, everything you do in space starts with, we want to go somewhere and do a thing. And where you can go and how much it costs and how long it takes and what you can do when you get there is entirely dominated by your propulsion and your power. And propulsion and power turn out to be closely interlinked topics. So if you are trying to solve some problem, and right now it looks too difficult or expensive, I just keep finding myself back at, okay, we're going to need better propulsion or better power. Otherwise we can't do the thing or can't afford to do the thing. So 25 years ago, that was reusable rockets. Everybody knew that rockets cost $1 billion to make and, could only be used once or the engines a few times. And, I wasn't convinced that that was true and went off and, I think demonstrated that that's not true. We made some progress in engines that I'm still not sure everybody in the industry is quite caught up to. And that we were doing small engines, but they didn't wear out. Our fleet leader engine, had 300 or 400 firings on it by the time that we finished, and it still looked brand new and ready to go. And they also didn't need maintenance in between flights, other than a couple of minutes of inspection. So, that was when 25 years ago, you asked the question, why can't you operate rockets with the speed and reliability of aircraft? And the answer quickly came, well, the engines won't do that. Well, it turned out the engines will do that if you ask them nicely.
Right.
Since I've been out of I don't do chemical rockets right now because there's not a lot left to do. The propulsion performance is as good as you can ask for from the chemistry. and other people have picked up the torch and are carrying the reusability aspects of it forward. So for Earth to orbit, which I'm still interested in, the nature of chemical rockets, reusable chemical rockets for Earth to orbit, is they can get very cheap if the traffic model gets very large. If people want to put lots and lots and lots of stuff into space, so you can build a sufficiently large fleet of reusable rockets and fly them every day, then the cost can get quite low. It's not, contrary to myth, it's not like the propellants are expensive or anything like that. It's just they're expensive ships, and if they spend most of their time sitting idle, they cost a lot of money. And if they spend most of their time, with the wheels in the wheel well, they can be cheap. And if it turns out that we're on the threshold of a dramatic expansion in traffic, then SpaceX will be able to lower the price, and competitors will be attracted into the market, and competitive pressures will push the price down, and all will be well. But
yeah, it's really basic economics.
Yeah.
Right? I mean, once you solve the technical problems of can you do this, like you said, the engines don't wear out, the inspection doesn't become an onerous and time-consuming process, then it's really just about packing the planes as full as possible.
Yes,
right?
but and I hope that totally works, because I would love to just move on from thinking about Earth orbit to all the other fun stuff that there is to talk about. But that might not happen, right? The volume of traffic that would be required to make something like Starship make economic sense, you'd need a couple hundred flights a year at 100 tons a flight minimum. That's what, 10,000, tens of thousands of tons. The current world market in commercial launch is hundreds of tons per year. So, I think in the fullness of time, that traffic will emerge. But, will that take a year or 10 years or 50 years before we reach those levels of traffic? That neither I nor anybody else knows. So if the just build it and they will come strategy works, Elon's got that covered. And I spend my time thinking about, okay, what if that doesn't work? Rather than just giving up, are there technical changes that we could make, different propulsion techniques that would not require such a large company? That's what makes these things expensive. It takes a company of 5,000 people to make these vehicles. That's where your overhead cost comes from. It has to be divided by many flights. Can we reduce the scale of going to orbit so that a much smaller company, or can we share most of the overhead costs with other non-space markets so that you don't have just space paying the freight? And that's what Electric Sky is about, is trying to find ways to kind of blend the high-speed point-to-point air transportation market with the space transportation market, because the air transportation market has all that traffic. So if you could find a way to serve Earth-to-Earth transportation needs through electrification or high speed or some other means that was competitive with subsonic aircraft, then you'd have a very large market, and space would have its costs borne by the larger traffic model.
It essentially sort of rides on the coattails of the terrestrial market demand, right?
So, but I would be thrilled if tomorrow, they said, okay, we've booked our first 10,000 tons a year. Then I'll go, great. I can move on to all the other stuff we want to talk about, which is more fun, which is what do you do after low Earth orbit is a done deal.
I definitely want to get into that. But before we go there, let's talk a little bit more about this conundrum. I mean, it is clear that Musk and probably Bezos as well are betting a large fraction of their company's future on the emergence of a large demand for Earth to orbit, in bulk, right? Not just small satellites, but the thousands to tens, hundreds of thousands, I guess, of tons per year that you're talking about. I guess we could prognosticate all day long about how and when and if that's going to materialize, but the basic drivers are you got to need to put a lot of stuff up there into orbit, and it sounds to me like it's a bit of a chicken and egg problem, right? You have to have the cheap launch to justify the demand, but the demand drives that.
Well, this is not a new problem, in history, right? All new transportation modes and services face this problem, right? The air traffic faced this exact same problem, right? It does no good to have airplanes if there's not a route of airlines that serve enough destinations that you have a place to fly from and to. As an individually chartered service of an airplane that carries one passenger at a time, it was not and never was going to be an economically viable model.
Right.
So, shipping to and from North America from Europe, in the 15th, 16th, 17th centuries was not a going concern because there weren't enough people on the North American end of the trading leg to make those voyages make economic sense. In both of those cases, governments stepped in one way or another to prime the pump and create, make a market to create a sufficient volume of initial traffic that operators would enter into the carriage, and until such time as there was enough economic activity to sustain the models on a free market basis. There's a huge opportunity for the United States to do that for 25 years, right? It's been 34 years, I think, since the U.S. denationalized space transportation. From 1962 to 1986, space transportation in the United States was just as nationalized as sugar in Cuba. If you wanted to fly a payload into space, you had to fly it on a U.S. government provided service. That was law as part of the National Space Transportation System, as the Space Shuttle was called in those days. And after 1986, that changed. And since then, there's been a huge opportunity because the U.S. government is a large purchaser of launch.
Right. They're kind of an anchor tenant, you might say,
yeah.
But they're certainly not the sole buyer by any
means.
No,
by no means. The U.S. Air Forces, the Department of Defense traffic in space is currently smaller than the U.S. commercial traffic in space. But the U.S. Air Force and other DoD entities have made the shift. They buy all their space launch services commercially, but from U.S. providers, of course, because it's Buy in America laws. But NASA does that for their robotic missions, and now they do that for their space station supply missions, but they do not yet do that for exploration missions, for human exploration missions.
Right.
And
human a very small part of the market, I guess, still, right?
Well, but in tons, it's potentially very large, right? That's the lost opportunity is that if you wanted to fly 2 Saturn V equivalent missions a year, that's 250 tons. That's a very large increment on the demand, even though it might only be a few flights of a large launch vehicle.
But there's a total mass launch to orbit that is
it's a difference that makes a difference, right? So instead of spending $3 billion a year on a government-only launch vehicle for government purposes,
right.
You could meet that same demand with 4 Falcon Heavies a year. 4 Falcon Heavies might not sound like much, but that's a lot of Falcon Heavies compared to the current traffic model.
Sure.
So it's a lost opportunity. I think in the fullness of time, people will get there because, we kind of can't really afford human exploration missions in the current model. That's why the programs get very stretched out in time, is because the budget really won't cover it, doing it the way that we're doing it right now. So you kind of have to push everything off. And, sooner or later, I like to think, maybe foolishly, that the taxpayers will desire some return on their spending, and start asking questions like, why are we spending $3 billion a year to do the job that 2 Falcon Heavies would do? Because 2 Falcon Heavies only cost $300 million instead of $3 billion. Maybe we could do something with the other $2.7 billion, like have a lunar lander that we could put on top of the launch vehicle. So, but we're not there.
Gotcha.
But
well,
there are things the U.S. government could do. There's other things they could do. There's not a lot of visionary leadership that views the problem in the light that we've talked about, of if only you had a sufficient stimulus to the market demand, the price would come down. It's still thought of as a mission activity rather than as a transportation activity.
I mean, there's a part of NASA, and we'll only stay here for a couple more minutes, and then I want to get into the other stuff. But there's a part of NASA that is very focused on wanting to grow the commercial market, at least in LEO, right? That shift happened several years ago. Their commercial crew and commercial cargo is a thing that is something that they are now turning the reins over to private industry, such as Orbital Assembly Corporation, as well as our several competitors, to build, fully commercial space stations in low Earth orbit. I mean, that's happening, but you're saying with the rest of NASA's mission, it's still very much driven by their own priorities, and maybe because it is premature, because opening the solar system to commercial activity is still a few years out, and it makes sense where they're at now. But I don't know. Do you have an opinion about that?
I mean, the dirty, not very secret about how ISS traffic became commercialized is that, the then administrator of NASA wanted to get rid of ISS. Congress wouldn't let him just splash it because he wanted to spend the money on what was then Ares. I forget the name of the program, but the thing the Ares wanted.
Constellation?
Yeah, Constellation.
Constellation version, right? Which is a heavy launch vehicle. Right?
Yes. So Congress wouldn't let him splash it, and meanwhile he was getting all these people making noises about commercialization. So the theory was, if we made the ISS dependent on commercial vehicles, and we made the bar for their commercial service extremely high, and we only wrote the contracts with like 1/10 the money that our cost models say it would take to build the system, they would be sure to fail.
Right.
And we could splash the ISS. But what happened is they didn't fail. And the world is different now.
Surprise, surprise.
But the problem with that trick is you can't play that twice, right? You couldn't. It's harder to justify turning over human exploration missions to private entities on the grounds that we're sure they'll fail, because they look more serious and credible now. The likelihood is that they would not fail, and if you turned it over to them, there would be an awful lot of established interest groups whose rice bowls would be upset.
Right. Yep.
But enough about NASA. It's depressing.
Yeah, it is. And we're here really to talk about, beyond any particular entity. Commercial is a large part of it, but really the big picture is just how might humanity move into the solar system, and what are the pieces of that vision that need to be realized and invested in the near to medium term. So with that, what you did in your career was kind of pivot toward looking at alternatives to heavy launch to Earth orbit, as well as looking beyond Earth orbit transportation. So why don't you tell us a little bit about that? What was sort of your big idea, or the thing that you're most excited about now?
Okay. Well, for Earth orbit, I won't spend long on it because I don't want this to be an advertisement for my for-profit activities. But we all have a living to make. I am working at Electric Sky on a beam power propulsion concept. And the idea is you beam power that takes the form of electricity rather than heat energy up to the vehicle, and you can use that for a variety of purposes. If you wanted to do atmospheric flight, you could turn propellers. If you want to do flight into higher altitudes, there's other propulsion systems that you can envision where you can turn that electricity into thrust pushing on the atmosphere. When you're pushing on the atmosphere, you don't have to carry propellant with you. So, 90% of the mass and volume of a launch vehicle right now is propellant. You're talking about if you if you were trying to do something like Dragon and you didn't need the Falcon underneath it, you could fit the thing in a garage. So that's interesting, but there are many technical challenges. We're at a very early stage.
I was going to say, this is not the first example of this idea being tried, and it's extremely difficult to pull off, but it is a sound concept with a lot of merit if you can.
The physics is good, the technology is daunting. So right. We're poking away at that with a little DARPA money right now, and that's what I do with most of my days.
Mm-hmm.
But about 6 years ago, I got approached to be the chairman of the board of the Tau Zero Foundation, whose charter is looking at advanced propulsion that has the potential to one day scale to interstellar flight. And that's an intriguing challenge for a lot of reasons. Interstellar flight is really, really hard. Like I could really to the nth, I could go on with a lot of reallys for a while. And why is interstellar flight hard? And that is, to do it in a practical way, you need to go really fast. Kinetic energy goes with velocity squared. So you start trying to go really fast, you have to get a lot of energy from somewhere. And that either takes a lot of hardware or it takes a lot of money, or usually both. But that's interesting. It has broad implications in two other ways, right? Everything I just said is equally true about flying around in the solar system at anything other than very low speeds, right? You'd like to go, it takes an inconveniently long time to do interplanetary flight. We'd like that to be faster. It takes a lot of money. We'd like that to be cheaper. That's an energy problem. It's the same problem. Furthermore, the big problems of civilization have this same character, right? Civilization is controlled and limited by how much energy can you conveniently get your hands on and convert into useful forms.
Right. When it was all done with your human power and animal power, there was a limit to how much you could transform your environment and improve the standard of living.
And that limit pretty much was Imperial China and Imperial Rome. That's about as much as you can do with solar power captured in the form of crops that you use to feed into muscles. And it's interesting sideline. I mean, people have really emotional feelings that go deep about land. Nation states are defined by their control of land. That's the whole concept of a nation state, is that's what defines it. Well, why is that? Well, that's because in the pre-industrial era, the only way you could get more energy was to own more land. The only form of energy that you got was crops. And so we still, centuries later, kind of haven't got fully adapted to the concept that there might be ways of getting energy other than just how much real estate you control. And we're talking about the amount of energy it takes to do even interplanetary flight is large enough that fossil fuels only get you so far. And at the meantime, our whole civilization is facing this question of fossil fuels can only get you so far. So it's very unlikely. It's a fruitful area of inquiry, because thinking about it in the context of interstellar and interplanetary flight frees you from the problem of, we would never be allowed to do X, Y, and Z because of this or that regulation. You're operating in a different domain.
The blue sky approach.
Look at the problem fresh, but it'd be very unlikely, I think, that we would find some breakthrough there and find it had no implications for our energy future closer to home, because energy, all forms of energy are interconvertible.
Right. There's almost always Earth-based applications of a new breakthrough. So,
and even if you can't think of a way to use the phenomenon on the Earth, you can always transmit the power using wireless power transfer back from space to the Earth, if you find some convenient way of harvesting large amounts of power in space.
As some people have suggested.
So that was an interesting charter, and what it led me to do was kind of spend a year or two getting to know the advanced propulsion world, and getting to know the people in it. It's a very small community. The annual conference has maybe like 200 people, or the biannual conference has maybe like 200 people that go. And for the whole field. I mean, the main conference of the year is the Interstellar Research Group's annual conference that happens every year and a half. It's a small group and everybody knows everybody. So kind of what I did is go get around and see what was happening and start looking for gaps. Where are there pieces that are missing, that if you had this piece, you could connect what person A is doing with what person B is doing, with what person C is doing, and get some interesting new capability. And to make a long story short, I got very fascinated by propulsion that comes from interacting with the solar wind. The solar wind, not everybody knows about it. Humanity's only known about it since the 1950s. It's a stream of plasma that boils off from the sun. And it gets accelerated in a very complicated way that we're still getting our arms around exactly how it works, by interacting with the magnetic field of the sun to quite high velocity. The solar wind leaves the sun at about 400 kilometers a second, or out in the plane of the ecliptic, and up out of the plane of the ecliptic at about 700 kilometers a second.
To put that in context, Jeff, for those who aren't familiar with these units, escape velocity from Earth is about 11
kilometers a second.
Right. And escape from the entire solar system is just over 40. I'm trying to remember the number.
Something like that. Yeah.
Yeah.
Voyager at its maximum velocity. Voyager is currently cruising in interstellar space at about 20 kilometers a second.
Right. And that's after having climbed out of the sun's gravity well, so it was traveling faster than that several decades ago. But the point is, this is much faster than that. So the solar wind is clearly leaving the solar system, but it's traveling at many times the velocity of current interstellar spacecraft.
Many times the fastest object ever made by a human. So that's interesting. Now, the challenge is it's very fluffy. It's very diffuse, thin plasma. So to interact with it in a propulsively useful way, you have to grab onto it with electric or magnetic fields rather than with physical objects, because otherwise the object would be so heavy, you would not get a useful acceleration out of it.
Right.
So there was some work done that I found out about by John Slow and others at the University of Washington on something called the Plaza Magnet. The Plaza Magnet is it's a little hard to simply explain. I have some videos on YouTube where I take half an hour to try to explain it.
Check those out.
Probably put a link to. But very simply, it's kind of an electric motor that's turned inside out. So instead of you have a small set of coils with a rotating magnetic field, and instead of turning a shaft with those, you grab onto the electrons that are present in the solar wind and pull them around the vehicle in a circulating motion. And what you've now done is induced a current, a circulating current, like a coil in the solar wind. And that coil is not confined by wires. There's no, it's just flowing electrons.
But because it's a plasma, you have a conductive medium that allows this to occur.
So when you have a circulating current, even in a coil of wire, there's a pressure on it. It's magnetic pressure that tries to make it expand. In this case, there's nothing resisting that expansion other than the pressure of the solar wind. So that loop of current expands quite dramatically from meters of coil to hundreds of kilometers potentially of field radius, until it comes into an equilibrium between the pressure that you're driving in it with the coils and the pressure of the solar wind. So you can get quite respectable accelerations on the order of 0.1 to 1 meter per second squared, or 100th to 1/10 of a g of acceleration that way without spending any propellant.
Boy, that is can I just stop you again and say that's a really impressive acceleration compared to, say, an ion engine, which is sort of
Yes.
the most efficient means we have when you're bringing all the power with you, right? And those accelerations are kind of in the milli-g range, if not less.
Yeah.
Mhm.
We did a study that's on one of the papers that we've discussed previous to the conversation. Brent Fries and I did a design study as part of our work on the AIAA Advanced Propulsion Group, and looked at doing a demonstrator mission and just a pure technology showcase. What can you do? To do it cheaply, we had to keep it solar powered. That's the one.
Yep.
Because a nuclear source would cost more than the rest of the mission 10 times over. And the being solar powered means you have to get all your acceleration done while you're in the inner solar system. So it does limit your performance somewhat. But we were still able to get something that would fly by Jupiter in about 3 weeks.
Wait, sorry, 3 weeks from launch from Earth?
Yeah.
Okay, so compared to the normal transit times for an interplanetary mission, years. So we're talking a flat factor of 50 speed up, something like that.
Something like that. Yeah,
On the order.
it'd be roughly Neptune in a year for transit time, as opposed to the whatever it is, 11 or 12 years that Voyager took with every gravity assist we could possibly dream up.
Right. Are people paying attention? This is really revolutionary if we can get this to work on scale.
Well,
I mean, this is like airplanes
I'm an
versus
evangelist for this
sail ships.
technology. It's not my idea, but I'm really excited by its potential. So I'm kind of beating the drum,
Sure.
trying to get people to pay attention to it. But we haven't, I haven't been successful in getting like a NASA contract or anything. The NASA, it's interesting, right? The outer planet, people think of NASA as the technology engine for space stuff, but their outer planet missions are done by a small group that, or actually not such a small group, but they're always done by the same people, right? So right now it takes them probably more than 10 years to get a mission concept sold in the funding pipeline, to get it on the decadal survey and get it approved and all of that stuff.
And there's a TRL issue as well, technology readiness level. So they don't want to fly something that's kind of at the experimental stage. They really want it to be almost flight proven or already flight proven.
Yeah, for very good reasons. They're very technically resistant. They don't want to introduce any new technology that they can possibly avoid, because they're only going to get one mission in their career.
Right.
So the idea of a propulsion technology that would make an outer planet mission something that you might do as a graduate student project, and it would be done in a couple of months, is not welcomed with the degree of enthusiasm that you might think, because that's a very dramatic change to the business model.
Sure, but so are CubeSats, right? Now that high school students can build and launch their own satellite, that's extremely disruptive too. But it's happening.
Yes, but you'll notice the CubeSats were not exactly funded by the people who are doing traditional satellites. And this probably won't be funded by the people who are doing traditional outer planet missions for the same reason.
Okay, but there's always a niche market that can get a new technology like this going, right? And I'm guessing that your first application isn't to send a probe to Jupiter, but maybe something a little closer to home, or what is?
Well, there is a challenge with this, in that in order to use the solar wind, you have to get out where the solar wind is, and the solar wind does not approach too closely to the Earth because it's held off by the magnetic field of the Earth.
Right.
In exactly the same way that this field we talked about generating for the ship would deflect the solar wind in order to push the ship.
Okay, so you got to get out of the sphere of influence, which is beyond the moon, basically.
Above 80,000 kilometers from the Earth before you can interact with solar wind, and that's on the sun side.
Right.
But if you did, there's a fun little mission that I haven't written up yet, but I've talked about it before. That altitude's about twice the altitude of geostationary orbit. So if you got out to that altitude on the sun side of the Earth, you'd pick up the solar wind. And if you did that while it was full moon, which is when the moon is on the night side of the Earth, you'd pick up so much velocity that you could reach the moon in about 16 hours. And then you could stop, because which is the hard part with these sails, because the wind only blows away from the sun. But in this case, you could stop because you'd be in the lee of the Earth. You'd be in what is called the magnetotail, the stagnant region of plasma that's caused by the shadow of the Earth stopping the solar wind. So you could then turn on the sail again as a drag device and stop, which would be a cheap and fast way of getting to the moon. So I continue to work on it, as does Brent, in our copious spare time. This is an all volunteer effort. But I'm intrigued, and we've gotten a little bit of interest from some of the folks who are looking at solar gravitational lens observation missions. The solar gravitational lens is a spot where the gravity of the sun bends the light from a distant object to a focal point, just like a lens would. Well, not just like a lens, but in a manner analogous to what a lens would do.
This is an effect of general relativity that any massive bodies, certainly the size of the sun or larger, I mean, any gravitating body, but especially those, are able to focus light. But it's quite far away. We're talking.
It's 550 astronomical units away, which is virtually out of reach for our current propulsion technologies. Right. At the speeds that this would offer, you'd be able to get out there in about 5 years. And what's not often appreciated about the solar gravitational lens is, to look at a different object, you have to be in a different place on the other side of the sun, right? The sun is your lens. If you want to look somewhere else, you have to move relative to your lens.
Yeah, and that's not a short distance out there.
It's not a short distance.
Yeah.
So practically speaking, you need a new mission for every new thing you want to look at. So for the solar gravitational lens to be useful, it's not enough to get out there fast. You also have to get out there cheap, because you're going to need to fly a lot of them.
Jeff, I'm going to stop you right now. I'm being told that there's some audio issue with my headphones, so I'm just going to switch out with some wired ones, and then we'll keep talking. We'll edit out this part of the interview. No worries. Okay, hang on a second. All right, can you hear me now?
Yes, I can.
All right, let's resume. Thank you for the comment in the chat about the issue. So we're talking about the solar gravitational lens and sort of demonstrate the real advantage of this fast propulsion technology. And you were just telling me that you would need more than one of these if you wanted to make practical use of it, because each mission can only observe one object in space.
One target. Yeah. So we've had some communications with those guys. We had a poster at one of the conferences. I think it's gaining a little visibility, but the ways of government are mysterious to mortal men. Who knows when and if we'll find customers for it. But in the meantime, I soldier on, and that concept led to others.
Okay. Tell me more. This is intriguing.
Okay. So once I came across this idea in the literature of harvesting the solar wind for propulsion, which was not my idea, I spent a long time trying to figure out, how do you stop? Right? I mentioned there's certain unique cases where there's a stagnant region that you can use to stop in, but in general, that's not true. In general, you're trying to stop in the solar wind. You can't use the solar wind to stop, because the wind only blows away.
Right.
Stopping involves thrusting towards the sun.
Okay. Mm-hmm.
And I struggled with that for a long time. I started working on that in about 2009, before I'd even gotten into all of this advanced propulsion stuff, just because of curiosity about it. And every year I'd kind of take it out and look at it and beat my head against it for a while and go, I can't see a way to do it. Finally, in 2019, I cracked it, which is, instead of using the solar wind as thrust, use it as power. In principle, if you have a wind, you can make a windmill, and you can extract energy from it instead of just extracting thrust from it. And if you use that energy to push reaction mass, like an electric rocket or a particle accelerator or something along those lines, now you have a propulsion system that has the interesting property that the faster you're going, the more power you have available, because that's the nature of wind energy. It scales with the speed of the wind.
Right.
So it's like a rocket whose specific impulse goes up the faster you're going, which is turns out to be very advantageous. And it's furthermore interesting because for travel inside the solar system, right, you're already starting at a high wind speed. So
even at rest with respect to the solar wind, you're saying, or I guess, yeah.
If you're at rest with respect to the sun, you're at very high speed with respect to the solar wind.
So you can collect that and in principle get a lot of energy right off the bat.
Yes.
Okay, I see.
So that led to what became called the wind drive or the Q drive. Q just because I'm an aerodynamics guy, and Q is the abbreviation for dynamic pressure.
Is this the right paper?
Yes.
Mm-hmm.
And in principle, that lets you do Neptune in a year, including stopping, or Saturn in about 4 months, including stopping. So you could do, a round trip to Titan in a year. Go out.
Unbelievable.
To Titan, stop. Be there for a couple months, wait for the return trajectory to come back, get started towards the sun, and then break using the solar wind again. And the propellant you have to spend is quite modest. The mass ratios are like 2. In other words, the mass of propellant, instead of being many times the mass of your payload, is on the same scale as the mass of your payload.
Okay, so let me just stop you for a second and understand. So it's not propellantless because this is what you're using to slow down, but the amount that you carry with you in order to essentially come to a standstill or to go into orbit around your target body, so it's virtually unmoving compared to the speed you were at getting out there, requires roughly equal mass to your payload. And
of that magnitude, yeah.
Okay, and then and that's just, I think many missions would just want to go there, do science, and then crash into Titan or whatever as the end of mission. But you're saying, but in addition, you could even imagine coming back, which opens up the possibility for sample return, or eventually, I guess, for human missions, bring the men and women home.
And if you wanted to do that, it'd be up to more like a mass ratio of the neighborhood of 4 or 5, which is still less than a third of the mass ratio that we associate with one stage of a chemical rocket.
Right.
And besides which, it's not fuel or oxidizer, it's just reaction mass. You're just something you're pushing. So there's really no reason you couldn't pick it up in the target system and use it to come home.
Oh, wow. Right. Sure.
Because it's nothing special about it. It's just something you're pushing out of your rocket.
You don't care what element it is, as long as it's something you can grab.
You'd need to design your propellant pusher to take whatever it is that you plan to use. But in principle, it doesn't matter very much what it is, as long as you've planned to use the thing that you're using.
Right.
No fluorine, please. But
for obvious reasons, kind of corrosive.
So that was that. I think that that was where that came up. That was developed because I couldn't solve this problem of stopping. And it was conceived and designed to solve the problem of stopping. As we talked earlier, I only think about propulsion in terms of, I got a thing I want done. How do I do the thing? But it turned out everything connects to everything else to have real implications for interstellar flight.
Mm-hmm.
Because if you're thrusting into the wind, all right, now imagine something else, whatever it might be, gets you leaving the solar system pretty fast. Okay, once you leave the solar system, you're in the interstellar medium and you're passing through it. So the wind is in your face, so to speak. And
it'll slow you down over a period of,
if you use the drag device, it would slow you down. But if you extract power from it and use to push propellant out the back,
you can keep going.
So it turns out that you can about multiply your speed leaving the solar system by a factor of about 4 or 5 this way. So it's not everything. You still need a way to get going halfway pretty fast. If you want to get 20% of the speed of light, you got to leave the solar system going 5% of the speed of light. So that's not easy. But it does bring the problem of interstellar flight down to a more tractable domain, because we have concepts for ways to leave the solar system at about 5% of the speed of light. A big fusion rocket, for example, would in principle get that job done. Whereas getting it up to 20% of the speed of light would be a very implausible mass ratio. So I was very hopeful about that, and that became, a series of talks that I've given at interstellar research group conferences and the like. And it gets better, right? This turns out to be a can of worms. Once you start looking in, there's all kinds of interesting implications, because
a good can of worms.
Once you start thinking about, okay, we're using the solar wind, we can extract power from it, and we can be pushed by it, right? There's a missing piece of the propulsion quadrant. Can you push on it, right? The way that we push on the air with propellers or jets or things like that. And it's like, okay, yeah,
you mean to get lift, essentially, is where you're going, or?
So what is lift? Okay, we think about lift in terms of a wing or a sail, but that's an implementation. What's the effect? What's the physical effect of lift? The physical effect is we have had a small amount of drag in the wind direction. We've used that drag to extract energy, and we've applied that energy to pushing laterally on the air in the direction perpendicular to the wind. Now, the wing is a machine that performs those functions. It extracts the energy, paying some drag, and using the energy to extract to push sideways on the air. And we all got stuck, right? Because people have been thinking about this for a long time. We all get stuck going, you can't make a wing, right? Number one, it's too diffuse. Number two, it's going hypersonic. You'd get skin friction drag. It just wouldn't work. But if you decompose the pieces, and instead of saying, I want to make a wing, what you say is, I want lift. If you take a windmill, which we've discussed already in the context of the Q drive, and you have a propeller at right angles to it, and you use the one to power the other, you've got lift. And that paper is still in prep publication, but my co-author and I, Andrew Higgins, gave a talk on, and Michael Rotary gave a talk on that at the last Interstellar Research Group conference. And that has some really interesting implications. One is, I think it's going to be wonderful for maneuvering around the inner solar system. In the inner solar system, your travel is mostly not so much a case of in and out as trying to get velocity prograde or retrograde going around the sun. So thrust at right, or lift at right angles to the wind is exactly what the doctor ordered for that.
Yes.
But it also is interesting because there's a phenomenon used by both people and nature called dynamic soaring. If you have a difference in wind speed and you can move across the boundary between the high speed and the low speed region, you can pick up energy. Soaring birds like albatrosses do this, moving in and out of the slow layer of air near the sea surface. This is what surfers are doing to gather energy, moving between two different regions of water speed.
Right.
This is how cosmic rays get accelerated between astrophysical shocks out in the universe, as they're bouncing back and forth between two regions that are moving with respect to each other. Well, we have a region like that at the edge of the solar system called the heliopause, where the solar wind is going hundreds of kilometers a second on one side of the boundary, and it's not on the other side of the boundary because it gets stopped by running into the interstellar medium.
Okay.
So you can bounce back and forth in principle between those two regions and pick up about 1.5 to 2% of the speed of light for free.
Wait, tell me, hold on. I thought we were about to speak about interplanetary, but now we're back to interstellar. So
I told you at the start, it's all the problems are all connected.
You just give it, so you just dropped this big clue. So all right, so you're out at the heliopause, you're bouncing back and forth across the boundary, and you're picking up speed each. So what's the analogy here? Is it like an albatross gliding on updrafts or something, or what would be?
Well, albatrosses glide in the speed difference between the fast wind that's far above the sea and the slow wind that's close to the surface of the sea.
Okay, sure.
But another way of thinking about it is, if you've ever seen the physics demonstration where you bounce a ball off of a moving object, right? You throw the ball at a moving plate, it ricochets, at more velocity than it started, because it, in the frame of reference of the plate,
it's moving faster.
It came in at a speed and it leaves at a speed, but the plate's moving.
Right.
If every time you turn around out in the interstellar medium, every time you get in the camera here, if every time you turn around out in the interstellar medium, you bounce off the solar wind, you pick up another increment of solar wind velocity every time you perform that maneuver.
Yeah, it's simple conservation of momentum is what you're describing, right? But it has to be done efficiently.
Yes, and so the lift over drag matters. It's not interesting unless your lift over drag can be reasonably high.
Okay.
So how much we're coming to the end of our window here.
There's no hard stop, Jeff.
Okay.
We're in the flow here, so let's just keep talking, and then
So that's interesting, both for interplanetary flight, especially in the inner solar system, where you have this problem of getting fast ahead in the direction circulating around the sun. A mission I'm dying to finish studying, but I just haven't had the time. To my mind, the holy grail of advanced propulsion is the fast round trip to Mars, because Mars is a particularly difficult problem for advanced propulsion. Right? When you see all of the breathless articles about, it's a slow news cycle, so we're going to pretend that we have some really good power supply and talk about what we could do with this magical electric rocket. If only we had the really good power supply to power it. Right. What they never talk about is that's a fast one-way trip. Right. You wait for 2 years for Mars to be at its closest point to the Earth, and then you sprint. But if you want to come back, you got to wait 2 years for it to come around again.
Right.
And that's not that helpful, right? What makes Mars a really challenging target for human beings right now is the long mission duration. You'd have to somehow keep these people alive for more than 2 years without resupply, without spare parts, without anything breaking that's really important.
Yeah. Not to mention the 6 to 8 months in 0G in a very confined space, and kind of not doing very much.
Well, in fairness, if you put them in 0G, you're guilty of medical malpractice. I mean, that's a mission design choice that you should never make. Never put people in 0G for 8 months. It's a bad plan.
Right. I think we would agree with you on
better
that.
than I do, but
yeah.
That's a case. That's not physics. That's bad mission design. But also there is a long exposure to galactic cosmic rays, and it's currently a lot of shielding mass, too much to be practical for chemical rockets to do something meaningful about that. So your choices are change propulsion to something that's more tolerant of your shielding mass, or go faster, or both.
Right.
Again, going fast one way isn't that much help, right? You got to get back.
That's right.
So the reason why the round trip is so challenging to do fast is Mars is in the wrong place, right? Even if you manage to go fast one way, Earth moves faster around the sun than Mars does. So if you get there fast, I don't really have one for Mars, but
well, Mars is on there. That's why I brought it up.
Okay.
The red circle is the Mars orbit.
Okay. So if you get there fast by going when it's close, by the time you want to come home, Earth's not anywhere nearby anymore. Earth's on the other side of the sun.
Right.
So getting there fast round trip requires you to do really high speeds, either prograde or retrograde, in the orbit direction, so that one way or the other or both, you can make up for this big angle difference between where the Earth and the sun are, Earth and Mars are relative to the sun. So it's a really hard problem. I'm optimistic that can be solved with the plasma soaring, but I don't know that yet. I can see that the vectors point the right way, but I haven't done the trajectory analysis.
Gotcha. Well, this might be a good time to just take a step back and maybe start to wrap up our conversation for today. We'd love to have you back, by the way, to maybe talk about some other things, since we didn't cover everything that we had planned, and also allow you to answer a few questions that have come in on the chat. But my step back is, our scope in this podcast is really to talk about how humans might live throughout the solar system one day. And I think that you've identified that fast interplanetary transport is both necessary and possible, and that we need not limit ourselves to just thinking about chemical rockets and multi-month or multi-year transport between the planetary systems. And maybe this is a good example here. This shows a trajectory that is very much orthogonal to the orbital vectors of Earth, Mars, and Jupiter on the outside, and it shows a 25-day one-way trip. That would be a fantastic way to connect.
That little thick part of the blue line is how far Earth moves during the trip.
Right. So you literally, if you just needed to go for a short amount of time on Jupiter, you could come back and Earth would not have moved that far. In any case, you'd be retracing your steps more or less the same. Very, very different if you're talking about classical orbital dynamics.
Yes.
So.
And when it comes to human beings, Titan is an incredibly interesting target. In many ways, for human occupancy, I think it's more interesting than Mars. It's the only body on the solar system that you can walk around on the surface without a pressure suit.
You still need oxygen, obviously.
You still need oxygen. You need one hell of a winter jacket. But you don't need a pressure suit. And if you could get there in a couple of months, including stopping, the nature of the outer planets is the optimum launch trajectory comes around again about once a year, so that you don't have this problem of Mars of the 2-year revisit time. If Titan were cheap to get to, we'd go.
Yeah. But if we could go to Titan, and notwithstanding the advantages, Titan's in the Saturn system, it's very far away. Anything closer, such as the main belt asteroids, especially as I'm thinking for resources, would be a piece of cake by comparison.
Oh yeah.
Not to mention NEOs, right, near Earth objects, and Mars, as we've been discussing. And
if you're pushing things even not very quickly, but doing so propellantless, by interacting with the surrounding medium,
right,
it moving larger amounts of material, as you might want to do for resource recovery, starts getting more interesting, because you don't have to scale up the mass of your mission to carry all of the additional propellant that it takes to move all the additional mass. You just have to wait a little longer.
Yes. But wait, what you're saying is the way you've described these missions, some propellant is required, but it's on the order of the payload. You can reduce that to almost zero if you're able to get the propellant at your destination, right? Like, let's say a carbonaceous asteroid.
Okay, but suppose now you want to, suppose you're gathering a lot of material at your target asteroid.
Right.
The interesting part of the mission propulsively happens when you come back. Because that's when you're moving the heavy thing, right? You move the light thing, you're just your mining machinery on the way out. Right? If you want to get down sun from an asteroid, that's equivalent to saying you want to apply some retrograde thrust.
Sorry, can you define down sun? You mean going toward the sun?
Towards the sun.
Yeah.
In system. Right, or upwind.
Right.
So what you want to do for that maneuver is you would like to get some propellantless retrograde thrust. You'd like to break the orbit so that the sun's gravity would pull you in.
I see.
Well, that's lift.
Yeah.
Which does not require propellant.
Right. At all. I mean, maybe you keep a little bit. I mean, we haven't talked about the nuances of fine-tuning your trajectory and that kind of thing.
Would get, and I don't know all the answers to that because it's very early days yet. I mean, we've just been discovering that these effects even might be possible. We're a long way from complete mission designs. You know, we could spend, graduate students can be spending a long time writing papers on the nuances of how we do navigation and trajectory control and whatnot. So there's a lot to do, but just for me, just getting to the point where I go, these things actually might be possible. They are allowed by physics, and there are avenues of approach for making the technology. It really changes your head about what you can and can't do. So many of the things that we've taken for granted are difficult, you know, are artifacts of the assumption that we're doing it with either chemical rockets or with electric thrusters based on very low specific power supplies. You know, and that might not be the only game in town.
Absolutely. You know, I think that might be a great place to end. And I've had a look at the questions, and really there's only one relevant question about which I'll just throw out. You know, I like to read the relevant questions. What is Mr. Greason's opinion on nuclear propulsion for deep space travel? This is from Aiden Hurley-Kalichi. You want to wait? I realize we haven't really been talking about carrying a power supply with us, but do you want to weigh in on that question anyway?
Nuclear is good. There's the short answer. For starters, we talked about propulsion, but I mentioned early in the conversation that it's really propulsion and power that govern what you can do, right? And in the outer solar system, nuclear power is nearly mandatory. It's you know, you get farther
much more energy dense
from the sun.
Yeah.
It's currently not widely appreciated that part of the reason we fly so few outer planet missions is we rely on a specific kind of nuclear power, a radioisotope thermal generator that's based on a certain plutonium isotope that we don't make bombs out of. And we don't have very much of it. It's a very limited supply. We can only get enough to fly one outer planet mission every other year. So and they cost a fortune. So doing something about that problem is equally important to propulsion. And small nuclear reactors are definitely one of the ways of solving that problem.
Right.
Nuclear propulsion comes in the flavors of nuclear thermal and nuclear electric, more or less. Nuclear thermal is relatively high thrust to weight, so potentially useful for things like going to Mars. It's not super high specific impulse. I mean, it's better than chemical, but not by a large factor.
Right.
A factor of 2 or maybe 3. Because it's a temperature limited process and we can't get the materials to get arbitrarily hot. Nuclear electric, you can get all the ISP that you want, but the conversion steps both carry machinery with them that adds weight, and more importantly, they have waste heat. So you have to carry radiators to keep them from getting too hot, and the radiators add a lot of mass.
Right.
So
this limits your overall propulsion efficiency because you're adding more and more weight.
But none of this is an argument against doing it. It's all there. It's all kind of scandalous how little reduction to practice we've made in that since it was essentially ready to fly in 1968. And I would absolutely love to see more done with it. I'm an all of the above guy when it comes to advanced propulsion.
Yeah.
But it's not a propulsion system in the same class of propulsion characteristics that we've been talking about today. It's an improvement over what we're doing now. We're absolutely ready to do it. We should do it. And what I've been talking about is what's after that.
Right. An order of magnitude improvement. Yeah. So let's keep that order. Well, thank you, Jeff. That is all the time we have today. So I want to thank everyone who joined the conversation or submitted questions, even those we couldn't answer, as well as to Jeff Greason. Thank you for sharing your time and your insight. And I look forward to having you back soon.
Thank you very much.
You're welcome. So if you have suggestions for future discussion topics or people you would like us to interview, please let us know by emailing us at ourfutureinspace@orbitalassembly.com, or finding us on Twitter at ourfuturespace, or Facebook at ourfutureinspace. Thanks very much, and we'll see you next time.